Well, today I have the honor to introduce the Dr. Jan Midtgaard, that holds a PhD degree from BRICS Department of Computer Science of the University of Aarhus. His research centers around the programming language and the technology surrounding. He has a particular expertise in functional programming language, static analysis based on abstract interpretation, and property-based testing. Today, I have the honor to introduce the keynote Adventures in Property-Based Testing. A PhD degree from BRICS Department of Computer Science of the University of Aarhus.
Thank you. So I'm sending to you from Denmark. Well, Denmark here it's a bit after 4 o'clock in the afternoon. As you perhaps can see behind me, it's getting dark. But as I understand, it's morning in Mexico, so I hope you will have a sunny and nice day down there. All right. Adventures in property-based testing. Well, we already meet the first challenge here, because if you try to search for material about property-based testing, say using Google, you'll have to use 2 different searches, one for property-based testing and the other one for QuickCheck. It's known under 2 different names. So that's the first challenge. So it's basically a form of randomized testing, and it started in the year 2000 by Claessen and Hughes. They presented a paper at the International Conference on Functional Programming, where they suggested this kind of testing library. So this was originally in terms of functional programming, but since then it has sort of spread out to many other programming languages, not only functional languages. So these days, if you look at the Wikipedia link there, you'll find over 30 different ports, so ports to over 30 different languages. There's even a commercial version of QuickCheck for property-based testing from a Swedish company called QuickCheck, which was funded by John Hughes, one of the original inventors. And so there are, I claim, a number of actually quite a few success stories of these techniques, and I want to try to share some of them with you today. So some of them are from academia, and some of them are applications from the Swedish company called QuickCheck. So academically, we could call property-based testing some form of random input conformance testing. So that sounds fancy, but what does it mean? Well, if you cut to the chase, so at the core, you describe tests using one generator. And the generator you can think of sort of as a stream. We can ask it for test input, and every time we ask it, we get a new test. We get a new random test input. And then the second part is a property, which you can think of sort of as an assertion. You may know from other languages. It's typically phrased as a function that takes one of these test inputs from the generator and then outputs a Boolean that says true, this property holds, or false, this property does not hold. And then underneath the hood, what you get from a property-based testing library is this kind of loop that will repeatedly ask the generator for an input. It will then test the property for that input. True, that went well. Okay, let's do it again. Try a new input, see if that holds. Okay, try again, until, well, you reach some bound, say 100 tests, or, maybe we find a counterexample. Here's actually some test input that invalidates that property. So since this setup is randomized, it's driven by a random seed. And so it can be useful to remember that seed if you want to rerun one of these test sequences. Say if you locate an error, you try to fix the bug, and then you want to rerun exactly that test sequence, then it's useful to remember that seed, or write it to a log file or something like that. Okay, so if that sounds sort of a bit abstract, let's do a concrete example. So it's the most stupid and simple example I can think of, but it's the simplest, well, that gets the point across. So the floor function. So many languages come with a floor function for rounding down numbers. What property should a floor function have? Well, we could say, well, the output, if we call floor, if we invoke floor, the result there should be less or equal than the input. Say, shouldn't that hold for any floating point number f we throw after it? Well, that's actually all we need now to write a complete test. So we needed two things, right? A generator and a property. And here the property, I've written that that mathematical property, I've translated that almost literally into code. So this is a function expecting an f and then doing that comparison. And float here is actually, well, it's the name of a type in this language, but it's also the name of a generator. So test.make here takes two arguments. It takes a generator and it takes a property. And lo and behold, that's a complete test for you. And then you can run it. And if your generator there has a reasonable probability of generating a corner case, such as, man, not a number, it turns out, well, that's actually a counterexample for you. So floor of not a number in this case gives back not a number again. And if you know IEEE floating point arithmetic, not a number is not comparable to itself. So that comparison up here actually does not hold. So have we located a bug already in floor? No, we had this idea of a specification, if you will, and it doesn't quite hold up, but at least it illustrates this idea of a counterexample and a property and a generator for you. All right, it gets more interesting, shrinking. But before I can tell you about that, I need to show you a bit more. So the generators, we saw the float generator, but you can also, these libraries come with sort of building blocks, so you can build bigger and more complex input data generators. And one is called list. So list here is a generator, and it takes as its argument a generator of the elements, of the list elements. So list int here, so int is again it's the name of a type, but it's also the name of a generator of integers. So list int gives us an integer list generator. And we can do that again, and then we can throw them both after pair, which is a generator of pairs that takes as its first argument a generator of first components, and as its second argument a generator of second components. So now, aha, we have built all of a sudden with very little code a generator of pairs of integer lists. So what should hold of such pairs? well, for any such pairs A and B, I've then written here a false property. It doesn't hold. And the property here that doesn't hold is if I glue the lists together. That's a list concatenation for you. So let's say we have the list 0, 1, and the list 2, 3. If I put them together, I get the list 0, 1, 2, 3, right? If I then reverse it, I get 3, 2, 1, 0, right? If I reverse each of these lists independently, I should get 1, 0 and 3, 2, right? And if I then put them together, I get 0, 1, 3, 2, which is not the same as 3, 2, 1, 0, right? Okay, so it doesn't hold. And so if we ask the PropertyBased Testing framework to find us a counterexample, and we disable the shrinking, this is what you get. And now I expect half of you to log off the stream and say, "This is the worst testing ever, Jan. We're not buying it." But I disabled what is called shrinking. So shrinking is test case reduction. And if I enable it again, using the same seed, this is the minimal counterexample that is reported to you as a user. So, well, only singleton list 0, singleton list 1. If we reverse them, they don't change any order. But if we then glue them together, we get 0, 1. And if we reverse, we get 1, 0. So that's the minimal example that you can find. So it's a locally minimal example that the property-based testing framework found for us. So we have the idea of a generator. We have the idea of a property. We have the idea of a counterexample to one of these properties. And now we also have this idea of shrinking, of test case reduction. Yeah, so in this case, the machine took 130 reductions, little simplifications to cut the counterexample down for us. But the nice thing was, it was not us as software engineers that had to manually cut down an input to, well, to try to locate what was causing the error. It was the machine doing the work for us. So that's nice. Okay. So the nice thing about reversal of lists and concatenating lists and floor and so on is that they are pure functions. They don't have any side effects. But a lot of code out there does have state internally. So how can we test code like that with property-based testing? Well, you saw this ability to generate a list. Now, if I write a list of commands, just symbolic commands, I can say, do an add, do a mem, do a remove, and then throw that after the list generator. I get a generator of lists of. How can we test code like that? Write a interpreter over the system that I want to test and say, here's a symbolic add, so let me call the add operation. And in this case, the example I have here is it could be a hash table. So I start by creating the hash table, and then, I see a symbolic add, so I call the add operation on the hash table. I see another add, so I call it again. I see a mem, so I query. Does this hash table have the element B? False, no. And I also write a second interpreter, this time over a simplistic abstraction, if you will, of the system. So a hash table I could model as an association list, so a list of key value pairs. That's a lot simpler than a hash table implementation that has hash functions and buckets and collisions and so on. It just sort of models the semantics, the intended meaning. So I interpret the add instruction over the model by adding that key value pair to my list. And again, and membership, I can query over my model. And then, now I have some output, both from my model and from my actual system. And so I can compare these two and see, do they agree? If not, well, at least I've located some disagreement between the actual system and my understanding of how it was supposed to work. So the nice thing here is that now we are no longer limited to the kind of combinations that one could come up with as a unit test writer, where we say, well, if I first add and then try to look up again, yeah, that's a good test. But we as humans are limited in our imagination. So our tests as a result are also limited by that imagination. But here, no more. We let the machine test all possible and impossible combinations. That's nice. All right. So with that basic introduction, I want to take you through a number of applications of this idea. And then eventually we'll talk a bit more about, well, the lessons learned and the bigger picture before I wrap up. So the first one is an example of testing a data structure, which is called a Patricia tree. So a Patricia tree is, I don't know if you know, a tree, so T-R-I-E data structure from your algorithms and data structures course. So a Patricia tree is sort of a bitwise tree, if you will. It can be used for representing both compactly and functionally a set of integers. And it can also be used for implementing maps where you have integer keys. So it works like this. At each internal node in this tree, there is a branching bit. So there's a 1 bit down here, and that means that all the numbers that have a 0 in this position goes in the left subtree, and all the ones that have a 1 go in the right subtree. Here's another branching node for you, and it says, this 4th bit, that's the bit that says, well, is there a number 8 here in the, so it's the 1s and the 2s and the 4s and the 8s, right? So again, the number here does not have that bit set, and the number down here at the right does have that bit set. So that's the basic idea of how you can represent a set 5, 8, 13 using such a Patricia tree. And you may have noticed that I don't have a lot of branching bits for testing between that 1st bit and the 4th bit. That's because the tree is compacted. So this prefix says here, anything in this subtree shares this prefix. So that's a Patricia tree for you. Yeah, so they came out in the late 60s, and then later they were sort of represented in a functional setting. So there is an implementation for this programming language, OCaml, that I've been using until now in the presentation. That library is used inside another library, which is actually used by an analyzer from Facebook. So people actually depend on this library. If you study the source code, you'll see that's non-trivial code, I claim. There's some logic here, testing bits and so on. So it's not at all immediately clear that this is correct. The thing is, there was actually a bug, and the bug went unnoticed for almost 20 years, and it was in a published paper. The thing, and I found it using these property-based testing techniques. So now I'll try to explain to you how. If we have an API like this, there's the ability to create an empty Patricia tree, or an empty set of numbers. We can do a singleton set, so a set with only one number. We can ask with mem whether something is a member. We can add an integer to an existing set, to move, union, intersection, and so on. So that should all be sort of straightforward. Now, the idea is that I want to generate not just sequences here, as we saw in the model approach, but trees, because I have these binary operations. There is union and intersection where I need two Patricia trees to union. So I'll generate arbitrary trees. So to do so, I can declare a little tree data type. So here it's in a functional language, but I hope it makes sense to you. There are 6 different cases corresponding to each of these operations that produce one of these sets. And now I can write a generator of these trees. And just to show you an example of what this could look like, it looks like this. So treegen here takes a parameter n, which you can think of as some amount of fuel. There's some gas that I have to work with. It's to limit my generator, so it will not go on infinite. So if I run out of gas, I'm in this case, and I say, now I only have the option to either generate the empty leaf node or a singleton. But if there's still gas in the tank, I have a number of options. I can choose between 6 different things. The 6 different things, I actually do weighting and say, I'll with a bit more higher probability, I'll generate the add case or the remove or the union or the intersection, and then with a slight lower probability, I'll generate the empty and singleton cases. And finally, yes, this is a recursive generator, but it's written sort of passing the recursive generator as an argument. So when I need to generate a recursive tree, I call argen, which is this parameter up here. And finally, I have parameterized the entire generator over my integer generator, which is what I then use for generating singletons and the add nodes and the remove nodes and so on. So what property should hold for these sets? So now we have a generator, right? What property should hold? Well, you may remember from school that sets should uphold associativity and commutativity and so on. And that's one valid approach to test this stuff. You could also do the model-based approach that we saw a sequential example of, where we write 2 interpreters, one over the API and another one over model. And then we check agreement between the 2. So what's a model then of sets? How about lists? If we are ambitious, we even keep them in sorted order. So this is the model implementation. That's a one-liner for the empty and the singleton cases, and similar for memory. And, well, okay, there's 2 lines there to fit it on the slides, and so on. But you see, it's a relatively simple implementation that hopefully should be clear, and much simpler than the actual bit fiddling logic of the data structure. And now we can run our tests. So here I ran 10,000 tests for each of these operations. I only ran 1 for the empty case because there's no need to retest that 10,000 times. In this case, I used a uniform generator for my integer generator. And so, I can even rerun that 10 times, and now we are up to 600,010 tests. So we start getting confident, right? Well, the last 50 years of software engineering just called, right? Testing. If you had a testing course, you probably learn test corner cases or boundary cases. What are the corner cases when you have this kind of bit fiddling data structure like the Patricia trees? Well, so in this setup, we should have the generator arbitrary int output them with some probability. So if we refine our integer generator here and say, okay, with weight 5 out of 9, I generate a small number. With weight 3 out of 9, that's 1/3. I generate just an arbitrary integer. And then in 1 out of 9 cases, I generate one of these extreme values, minimum integer or maximum integer. Then what? Well, then I at least have a reasonable chance of generating both duplicate numbers and these boundary cases. And then, boom, if you rerun, this is the counter example for you. So that's, 2 add instructions. And if you do union for those, both over the system under test, the Patricia Tree module, and our model, there's disagreement. So if you union those and you don't get mean int 0 and 1 as a set, what do you get? In the implementation, you actually got a duplication of mean int in the output. And that's not a set anymore, right? That's some people call that a multiset. Yeah. And the problem, it turns out, is that there is a signed comparison over these branching bits that we talked about. And that confuses, well, the situation where the branching bit is the sign bit itself. I showed this example to the author of this library, Jean-Christophe Filiatre, and in no time he had an elegant fix where you could use this specialized comparison function instead. And so if you fix it like this and rerun the tests multiple times, the issue goes away. So if you're curious, the code for this example is online at GitHub. So you'll find the URL there. There's this guy called Simon Kruyanis. He had another implementation of Patricia trees. So the nice thing is he could reuse this model if he just changed one interpreter to call his library instead. So if you're curious, the code for all right, so that concludes the first example that I wanted to show to you. The second one is WebAssembly. So WebAssembly, that's a portable assembly language. It's supported in 4 major browsers these days. So the nice thing is, here's a little web example module for you. So you see get local I32 add. So get local will push things onto the stack, and then add will take them from the stack. So you have a stack-based mode of computation here. You also see type annotations. Parameter I32, so there are types in here. So it's a statically typed language. And then when this runs inside a browser, the WebAssembly can import and export functions from the surrounding context. So that would be JavaScript running in the browser. So you have a stack-based. So in order for WebAssembly to be a success, of course, it should behave the same whether you run it on Firefox or Edge or Safari or Chrome. And so the people behind it have really gone out of their way to ensure consistency. So there's a formal type system that describes this kind of module validation that you need. There's a formal semantics. There's even a formalization of these things inside a proof assistant called Isabelle. There's a reference interpreter mimicking the formal semantics, and there are thousands of unit tests. So you might wonder, well, with all that effort, it must be enough. Well, no. So here's a counter example for you. If you run that in Chrome or V8, which is the JavaScript engine and WebAssembly engine inside Chrome, and with JavaScript Core inside Safari, and with Chakra, which was the engine inside Edge, at least until last year, you all get a successful run. However, if you run it with SpiderMonkey, which is the engine inside Firefox, you got a crash. Well, these until we found it and reported it. You can see the URL there. Yeah, Jan. Well, that's the thing. We didn't write this test program by hand. We generated it. And so we are using this traditional property-based testing loop to test WebAssembly engines. So we have written a generator of WebAssembly modules, and then we have a property that says, is this module consistently interpreted over all these engines? If so, well, let's try another one. Let's try another one. Let's try another one until we find some counterexamples. So WebAssembly has 4 basic value types. There's 32 and 64-bit integers, 32 and 64-bit floating point numbers. It has locals and global variables. It has a memory, which is sort of a sequential block of memory locations. These can be initialized with what is called data segments. You can have you can have functions. You already saw one of them. You can designate a special one of them as the start function, which is sort of similar to a main in Java or C. And then you can have tables of functions, which are then initialized with what is called element segments. So with all of that, we can start understanding that Firefox bug that you saw as there's a empty function. We designate that as the start function. Then we declare a table containing only one function, and then we initialize with one of these elements segment initializers at offset 0 function number 0. And that was all that's needed to trigger this bug. Of course, so both the functions and the global variables and tables and the memories can be imported and exported from the surrounding context, say JavaScript. Yeah. So the modules, the WebAssembly modules, they are validated before they are run, and that validation check is expressed declaratively with a formal type system of this form. So I've only included sort of a selection of the rules. There are many more. But say if we look at the binary operation bin up down here, you'll see it expects 2 things. Like we saw i32.add, which would add 2 32-bit numbers on the stack. So it expects 2 things of the same type on the stack, and so the result will be only one of these that will be the sum. So that's an example of this formal specification for you. Yeah. So what you'll notice is that this describes stack changes really. I expect at least these 2 things on the stack, and I will promise to return one of these on the stack when I'm done executing successfully. So there's a typing rule similarly for functions in WebAssembly. And so if we look at that formal specification as a relation and then say, let's write a generator as a function following that specification. Well, the context here, that's the context of the general type checker or validator. We extend the arguments of the function. Well, annotating them as local variables now. We record with a label saying, if I ever exit, I expect these return types on the stack, and also record, when I return successfully, this is what I expect on the stack.
Annotating them as local variables now.
So in this setup, the value type that we supply is really a parameter to our generator. Can you generate me a body for this function, a random body that has this resulting type?
Successfully,
and int here is again a fuel parameter to limit the generation, as you saw in the Patricia Tree example. And finally, my generator here then returns an option type that says, was this successful? Was this generation attempt successful or not? So you get a backtracking generator if you write it like this. And Palka and others have done something like that for a simpler type system. So the interesting thing here is that since we start from the result type or the result stack shape, we actually get a generator which will try to generate programs starting from the back and then completing to the track. So more generally, this is the recipe that our generator follows. We start by generating this context with a memory and a table and globals and initializers for them, function signatures for what functions should be in the module, data segment initializers, element segment initializers, and then lastly, we generate the function bodies so that we can generate function bodies that can refer to both the global variables and the memory and the table and the other functions, and perhaps the function itself if we want to generate recursive functions.
What functions should
Yeah.
be in the module?
All right.
Data segment
Well, that works actually surprisingly, but the programs you get quickly becomes terrible to look at. So we've implemented a shrinker as well. And so that's a standard shrinker similar to what we've talked about so far. So once we get a counterexample to this consistency property, the shrinker will then try to reduce the programs down to something minimal, one little reduction at a time, and check for each step, is this still a counterexample? Is this still inconsistently interpreted by these different engines? And at some point, if it cannot cut down any further, well, we get a locally minimal counterexample. It says, this is the minimal module that I could find for you. And to do so, it combines a number of different heuristics. So we can try to eliminate functions and imports and exports which are not needed. We can try something very aggressive and try to reduce an entire function body just down to one constant, or perhaps just an empty body if this is a void function. Or we could try something more complex that tries to pattern match on, if I get one const and one add, I can substitute them perhaps just by one const while keeping the stack shape identical. And then you can do a number of other things, cut down the number of globals, reduce the tables and the memories and so on. So to give you an example of how that works, here's a log of one of these counterexamples our generator found. It's too big even to fit on the slide, but I just show it to you and then switch slides here as initially it tries to cut down functions. Then eventually it starts, you see a body there being reduced. Here's some body reduction being done, some more body simplification. Oh, here an if was removed. More simplification, more simplification, more simplification inside the functions. Now we could simplify even more. And now more. And now I think the globals are starting to be eliminated, the memory, and so on. And now, that's the output example for you after all these reduction steps. And I hope you agree that as a software engineer, this is much easier to work with as a bug report. So in order for all this to work, we have programmed a setup that looks something like this. Each module exports 3 functions from the WebAssembly module and prints the result. It also imports from JavaScript 3 printing functions for different number types to get some output for us to compare. And then we have this pipeline where we, for each generated module, we say, we first convert it to sort of a self-contained JavaScript file that then embeds that WebAssembly program. And then we run it with SpiderMonkey and V8 and JavaScript Core and Chakra. And because we have the option of generating infinite loops or recursive functions, we run things with a timeout. We log all these outputs to a file, and then in the end, we compare them. And we also actually hook into the reference interpreter to compare to that, but I haven't illustrated that on this video. So there's a lot of challenges to do something like that. Just starting with printing, we are just running these engines from the command line. So we don't have console log. Eventually, we found something called print, which is supported by all 4 engines, but it's actually not standard ECMAScript function. Different engines will also throw different error messages. How do we go about that then? Well, we normalize them. We try to normalize them using regular expressions down to something comparable, and so on. Just printing floating point numbers, well, the engines actually compute the same bit patterns, but once we print them in base 10, they use different algorithms, which means there's different output. Eventually, we ended up printing in base 2, and that solved the issue, and there are more problems. But we found a number of things using this approach. I've listed them here. I'm starting to run a bit low on time, so I'll just show you another example. There's a branch table issue for JavaScript Core, which is the one inside Safari. This example would run fine in all other 3 engines, except that in JavaScript Core, it would loop. And that's the idea of this branching table. It would branch, it should branch to label 1, which is the surrounding function context, so finishing the function. But what it actually did was just branch 1 label out and then restarting the loop. And it's it's not just an academic issue, because there were users out there which were affected by this, because all of a sudden their product had font rendering issues. So there's an issue link there for you to look at. Yeah. So here I tried to illustrate that you could use property-based testing for stack directed program generation and shrinking of WebAssembly. And so I hope I convinced you that you could actually find something here. There's a link there also to the code on GitHub if you are interested in hearing more about this. So these days, so third application, REST APIs. You probably have encountered something like that in your studies, or perhaps as programmers. We can play the same game of model-based testing over REST API. So if we have some endpoints, post, get, delete, get, well, then we could write a generator of symbolic commands and then interpret them over the REST API, right? After we have started the web server, and then we can write a little model. just like we did before. So for each symbolic command, we perform the actual HTTP request. And then once we get something back, well, HTTP responses have a status code and a response headers, and sometimes they also have a body with data. And then we can compare these up against our model. And so I've used this in assignments in a course on web technology, but I've also had students that tested company products from 2 different companies, one within healthcare, another within defense, and the third one within e-commerce. And they've actually found issues in all these REST APIs. So there are a number of other applications. One successful one, it's not worked by me, but it's an impressive piece of work. So in Volvo cars, they rely on this AUTOSAR standard. And that's a 3,000-page PDF specification for you. So in this other work, these researchers from Chalmers and QuickCheck actually wrote models, as we've talked about, of each of these module specifications from the AUTOSAR specification and tested them. And then once you had modules that depended on others, they started doing integration testing where models were combined with actual modules from the system under test to test things in context. And here's an example bug for you that they found in one of these modules, but I don't think I have time to cover it. There are a number of other applications out there. All right, so what can you learn from this? Well, if you want to use this, it's natural to think, I want equal chance of running all tests. Well, no, actually not. The 50 years of software engineering was telling us, we have to have a generator that has perhaps a greater chance of generating the boundary cases. So that's an argument for doing sort of a skewed distribution. It does not, every output does not have equal chance, but every output has some chance. If you do this, it will only be as good as your generators. In our case, we had uniform generators with very little chance of generating duplicate numbers. But once we had that and duplicate extreme cases like the mean int, we found it. It will also only be as good as your properties, but that sounds a bit lame, so we can rephrase it. You get answers to the questions you ask. So since I'm only generating, say, for the WebAssembly valid modules, there could still be a bug related to some engine that would erroneously accept an invalid module, say. That the floor function's output is less or equal than its input for everything but not a number is still not a guarantee that it's correct. That would be satisfied by the identity function, say. So it's the stronger property you have, the greater the chance of finding a counterexample there will be. Yeah. All right. So graphically, a program execution, you probably already know this. Well, you can think of that as a trace between in some space of executions. A different input could give rise to a different test. And formally, you can describe this in formal methods and formal semantics as a collecting semantics. So no testing talk without the famous quote from Dijkstra: program testing can be used to show the presence of bugs, but never to show their absence. So yeah, So if we're lucky to write that test by hand that triggers the bug, we know of it, but otherwise we don't. The nice thing about the property-based tests is that they are not as limited by the human resources. If we want to run 1,000 tests rather than 100, or if we want to run 100,000 tests, it's just a number, it's a parameter, so we crank it up. So we get a better under-approximation of all the reachable traces. And that means, well, we have a bigger chance of finding bugs. Yes. And I claim that that fits nicely into the software development setup. The floor function was an example of a unit test level. Patricia trees were sort of more on the component level. The WebAssembly was more on the functional level. We were just from the outside giving a full program, and then the AutoSAR example, they actually both did integration and multiple other levels. So I hope that I have convinced you at least that, well, property-based testing is an approach to randomized automatized testing. It focuses on these more high-level properties, which can either be domain-specific or this general idea of agreement with the module. The nice thing is it can shrink counterexamples down to a minimum. And, well, it actually applies to multiple levels of the testing spectrum. There are a number of applications and libraries, but I didn't have time to cover them. So the moral of the story is don't write tests, generate them. And if you are interested in this stuff, I actually have funding for a PhD student to work with me on this. So if you're curious, I invite you to look at that link, or otherwise you are welcome to contact me. Thank you.
Thank you, Dr. Midtgaard, for your interesting presentation. Now we will have a bit of time for questions from the public, and I guess we will wait for some questions. Okay, here are some questions about what other applications are potential for PBT?
Well, yeah, so I didn't so there have been a number of applications. So these are sort of from the research literature, but in this first one on this list, they used it to test protocols for telecom, so telecommunication. In a completely different setting, say, I have a good colleague that have used it to test very domain-specific properties within something like computational geometry. And he actually managed to find a bug in a textbook algorithm that way. So once you start thinking about, how can what properties should generally hold, and how could I generate input for this domain? I think there are very, very few limitations, actually.
Thank you, Doctor. Another question is, how we integrate a form of PBT on parametric AI explainability?
Ooh. Parametric AI explainability. That's a big question. I don't know too much about AI explainability. In some sense, I would say that well, as far as I understand, at least in AI, some people use sort of generation techniques to train, say, a neural network. So you have one thing that will try to generate things, input for an AI, and then train it on that generated data, so that you don't have to collect and annotate a big data collection manually. So some of these generation techniques already are used, I know, in AI, but yes.
Thank you so much. Another question is, the edge cases need to be human specified or need to be known?
Yes. Well, in some sense, at least as I presented it here, we as software engineers have to think of edge cases like we do when we would write unit tests. The thing is that now, if we have a generator that includes these, say, for strings, there could be special characters. Well, we can write that generator once, that string generator, including some special characters, or the integer generator that includes some extreme values like min int and max int, and then you can reuse it. So the generator becomes a reusable component. So if we move to a different domain, well, the boundary cases tend to pop up again and again. So one example, you saw the Patricia trees, there was min int, a duplication was actually triggering the bug. And in the WebAssembly case, there was this function 0 that was both in a function table and as a start function. And that was actually also the duplication. So there are these general patterns of boundary cases, duplicate values that pop up again and again. But if you've spent the time, and some of the best libraries out there for property-based testing already have generators that include these extreme or boundary cases, so you don't have to think about them. There's a very good library for Python, say, that it is called the Hypothesis, and it has very nice generators built in. So I've had students that used that successfully, and then they found bugs on boundary cases that they didn't have to think about because they were just reusing that software engineering that has gone into that framework.
Okay, thank you so much. I guess that is all the question. Then, well, I finally am glad to give the next certificate, and I will try to share part of my screen to show the certificate. Well, I cannot share the certificate at the time as you present your slides, but it's okay, okay, okay. Thank you. Um, uh, well, there is the certificate. Uh, Entrego la constancia de participación a el doctor Jan Midtgaard por su participación como ponente magistral en el marco del 20º Congreso Internacional en las Ciencias de Computación, por su conferencia titulada Adventures in Property-Based Testing. Well,
Thank
thank you
you.
for your keynote, Dr. Midtgaard, and thank you so much for being here today. And I guess that's all.
Thank you for the invitation and thank you for listening.